Hello everyone, I'm Shi Yang. Today I'm going to present our work, SHINE-PPG Non-Lambertian Intrinsic Decomposition for Illumination-Robust rPPG. rPPG is a contactless technique that estimates physiological signals from facial videos. It captures subtle skin color variations caused by volume changes. We use these variations to obtain an rPPG waveform and estimate heart rate. However, these subtle physiological signals are highly sensitive to illumination variations. Lighting conditions can also differ significantly across datasets, especially between control environments and challenging driving scenarios. This makes cross-domain generalization particularly difficult. Our key idea is to disentangle lighting interference from skin appearance. Conventional retinists decompose the image into illumination and reflectance, but it does not consider specular highlights. These highlights are strong reflections from the light source on the face, which can interfere with the subtle skin color variation that carry the physiological signal. Therefore, we adopt non-Lambertian formulation that explicitly models reflectance, illumination, and specular highlights. Our method consists of two parts: self-supervised non-Lambertian decomposition and adversarial illumination enhancement. Let me first introduce how we learn the decomposition without additional labels. The first part aims to remove lighting interference while preserving the physiological signal. Since we do not have the ground truth decomposition label, we generate paired videos using color jitter with different lighting but the same face. Both videos are then decomposed into reflectance, illumination, and specular components through three separate branches. Next, we design the loss terms based on the characteristic of each component. For reflectance, since the paired videos contain the same face, their estimated reflectance should remain consistent. We further use spatial frequency prior to separate reflectance from illumination. Reflectance contains more high-frequency facial details, while illumination mainly varies at lower spatial frequencies. This difference helps the model disentangle the two components. For specular highlights, we constrain spatial sparsity, concentration in the bright regions, and color consistency with the light source. These constraints help isolate specular highlights from the face. A reconstruction loss keeps the decomposition consistent with our non-Lambertian decomposition model. Finally, we use negative Pearson loss to preserve the physiological signal in the reflectance branch. Next, we simulate lighting beyond the training domain. With the rPPG model fixed, the learnable ADA-in module generates challenging illumination by maximizing the prediction error. Then, we fix ADA-in and train the rPPG model to minimize the same error. This adversarial process improves robustness to unseen illumination. In experiments, we evaluate SHINE-PPG on 5 datasets. An MRNRP car is the most challenging because its driving protocol contains complex illumination variations. On MRNRP car, SHINE-PPG achieves an MAE of 1.68 bits per minute. More importantly, under PURE2 car cross-domain testing, it achieves a correlation of 0.74, showing strong generalization. Finally, compared with conventional retinics, our non-Lambertian decomposition better preserves facial appearance and avoids the white artifact caused by specular interference. Also, we visualize the estimated rPPG signal under and overexposed conditions, while this formula is strongly affected by the illumination and predicts an incorrect R rate. SHINE-PPG better follows the ground truth signal and correctly estimates 80 bits per minute. Thank you for listening.